Hello, welcome back. In our last lectures, we explored the Lorentz force, how magnetic fields affect moving charged particles, and the force experienced by a current-carrying wire in a magnetic field. Now it is time to combine these concepts to understand the magnetic force on a closed loop of current. This concept is important in devices like electric motors where magnetic forces create rotation. Let's start by thinking about a rectangular loop carrying a steady current in a magnetic field and analyze the forces on each segment of this loop. Consider a rectangular loop with current I with two sides of length A and the other two of length B. Let's place the loop in the xy plane so that it lies flat on any center at the origin. Let's also assume that the magnetic field B is uniform and points along the y-axis. B is equal to B j hat. The loop is composed of four straight segments, each of which will feel a force due to the magnetic field. Using the formula for the magnetic force on a current-carrying wire, F is IL cross product B, where L is the vector along the length of the wire segment. Then let's calculate the force on each of the four segments individually. Segment 1 lying along the x-axis from minus a over 2 to plus a over 2. Length A directed along the I hat with current I. The force on this segment is F1 is IA I hat times B j hat. This force points in the Z direction upward out of the plane. Segment 2 along the y-axis from minus b over 2 to plus b over 2. The length is b directed along the j hat with current I. The force on this segment is 0. Since L vector and V vector are parallel, the force on this segment is 0. Segment 3 along the minus x-axis from a over 2 to minus a over 2. Length A directed along the minus I hat with current minus I. F3 is equals to minus IB k hat, which is the same as minus F1. This force points in the minus Z direction downward, opposite to F1. Segment 4 along the minus y-axis from plus b over 2 to minus b over 2, and it is 0, the net force on this segment. This segment also experiences 0 force as L vector and B vector are again parallel or anti-parallel in this case. Adding up the forces from each segment, we find that the net force is F1 plus F2 plus F3 plus F4, which is 0. Thus, the net force on the closed loop in a uniform magnetic field is 0. However, the loop may still experience a torque, which can cause it to rotate in the magnetic field. Let's examine the forces in terms of positioning on the loop. Segment 1 feels a force F1 directed out of the page along Z. Segment 3 feels an equal and opposite force F3 directed into the page along minus Z. Since these forces are opposite but act at different points on opposite sides of the loop, they create a torque about the center of the loop. This torque will tend to rotate the loop. Let's determine the torque exerted by the forces on segments 1 and 3. For a force F acting on a distance r from the axis, the torque tau is given by tau is equals to r cross product F. So the torque from F1, so it's the force is F1, IAB hat, k hat, acts at the distance of b over 2 from the center of the loop along the y-axis. The torque from F1 is given by tau1 is equals to b over 2 cross product IAB, and this product is IABB over 2 in the minus I hat direction. We can do the same exactly for force 3, and we get that the torque from the force 3 is minus B over 2 J hat times minus IAB K hat. The total torque on this loop is the sum of torque 1 plus torque 3, so the net torque is IABB minus I hat. So the loop experiences a torque of magnitude IABB directed along the minus x-axis. This torque rotates the loop, attempting to align it so that the plane of the loop is perpendicular to the magnetic field. So, a current carrying closed loop in a uniform magnetic field experiences zero net force but may experience a torque. The torque tends to rotate the loop to align it with the magnetic field, with the plane of the loop being perpendicular to the magnetic field B. The torque on a current loop forms the basis for electric motors where magnetic fields interact with current loops to create rotational motion. Additionally, galvanometers and odometers rely on magnetic torque to measure current by observing the rotation of a loop in a magnetic field. So, by analyzing the magnetic force and torque on a closed current loop in a uniform magnetic field, we see that while the net force is zero, the loop can still experience a torque that aligns it with the magnetic field. This torque is central to technologies that convert electrical energy into mechanical energy. Let me know the questions you have in the comments below, and may science be with you.